Somewhere in the North Atlantic, a current that has run for more than 10,000 years is drifting off course. Not by miles, by 33 miles. And that number, 53 kilometers since 1993, is not a measurement of speed or temperature or salinity. It is a measurement of position. The Gulf Stream is in the wrong place. And a team at Utrecht University just matched that shift to a signature they found in a simulation. A signature that only appears at one specific moment in the life of an ocean system approaching collapse. Stage 1. To understand why that matters, you need to know what Utrecht actually built. The simulation took 6 months to run on one of the most powerful supercomputers in Europe. A laptop doing the same calculation would finish in 14 million years. The resolution, the granularity, how finely it carved the Atlantic into cells of water and modeled what each one did, was higher than anything attempted before on this system. And when it ran, it found something no previous model had ever captured: a two-stage collapse. Not a gradual fade, not a smooth decline, a long, slow drift lasting roughly 400 years, followed by a total failure in approximately 2 years. That is the second stage. 4 centuries of slow drift, then a system that moves heat from the tropics to the North Atlantic, a system that shapes winters in Europe, monsoon patterns in West Africa, rainfall across the Amazon, sea levels on the American East Coast, fails completely in 2 years. That 2-year number is the loop we'll close. But first, the thing that makes this simulation different from every model that came before it is not just the resolution or the computing time. It is that the two-stage shape it found left a fingerprint. A specific, measurable signature in ocean behavior that marks the transition from stability into stage 1. A kind of early warning signal that, in theory, you could look for in real observational data. So they looked, and the Gulf Stream, the surface expression of the system this simulation modeled, has been drifting northward at a rate and in a direction that matches stage 1 of that signature. 30 years of satellite and oceanographic data, and it lines up. Not approximately. Not within the margin of a rough comparison. It lines up with the pattern the model said you would see if the Atlantic Meridional overturning circulation had already entered the first phase of its collapse sequence. Stage 1 is not collapse. That distinction matters, and we'll come back to it. But stage 1 is also not a warning that collapse might happen. It is the process already running. The question the Utrecht result forces is no longer whether this system can tip. It is where in the sequence the real ocean currently sits, and what, exactly, the world looks like if stage 2 arrives on the schedule the simulation found. To understand what stage 2 would mean, you have to understand what the system actually does. Not in abstract terms, in physical ones. Because the Atlantic Meridional overturning circulation is not a metaphor for climate risk. It is a heat pump the size of an ocean, and a significant fraction of the northern hemisphere runs on it. Here is the mechanism, stripped to its bones. Warm, salty water flows north along the surface from the tropics. The Gulf Stream is the most visible piece of this, carrying heat poleward. As it moves north, it loses that heat to the atmosphere. Western Europe absorbs most of it. Then the water, now cooled and dense, sinks. It sinks deep, travels south along the ocean floor, and eventually resurfaces thousands of miles away to start the loop again. That loop is continuous, and it is massive. At its peak throughput, the AMOC moves roughly 17 million cubic meters of water per second, more than 100 Amazon rivers, running simultaneously in a single connected current. Oslo is level with southern Alaska. The reason those cities are not tundra is the AMOC, delivering heat that has no business being that far north. Climate models consistently find that without it, average winter temperatures across northern Europe drop somewhere between 5 and 15 degrees Celsius. That is not a rough estimate. That is the gap between the climate those countries currently farm and plan around, and something closer to a different continent. The consequences don't stop at European winters. The AMOC also anchors the position of the tropical rain belts. The West African and South Asian monsoons, systems that deliver water to roughly 2 billion people, are sensitive to the north-south temperature gradient the circulation maintains. Weaken that gradient and the monsoons shift. Historical collapses of the AMOC during the last ice age moved the African monsoon southward by hundreds of kilometers. What had been farmable land became desert. What had been desert flooded. And then there is the coastline problem. The AMOC acts as a drain. It pulls water away from the US East Coast and into the interior of the Atlantic. Shut it down, and that drainage stops. Sea level along the eastern seaboard, Boston, New York, Miami, rises by an additional meter or more, on top of whatever warming-driven sea level rise is already coming. The cities most exposed to that outcome are also the cities currently building seawalls against a much smaller number. This is the system the Utrecht simulation modeled. Not a peripheral player in Earth's climate, a load-bearing structure. And what their data suggested was that this structure does not weaken gradually towards some distant theoretical threshold. It has a shape to its failure, which raises the obvious question, how long have we known it could fail at all? The honest answer is, a long time. Long enough that the gap between what scientists knew and what they could prove became its own kind of crisis. The first serious evidence that the AMOC had weakened came in the early 2000s. Researchers analyzing deep-sea sediment cores, essentially drilling into the ocean floor and reading centuries of Atlantic circulation history like tree rings, found that the current was measurably slower than at any point in the last 1,000 years. Not a model prediction. A measurement from the record already written in the rock. Then in 2004, the UK launched RAPID, a permanent array of sensors stretched across the Atlantic at 26 degrees north, roughly level with Florida. For the first time, scientists had a continuous instrument reading the AMOC's strength in near real time. What RAPID showed over the years that followed was a system fluctuating but trending weaker. By 2012, a significant short-term slowdown had been recorded. By 2021, an analysis of proxy data going back 1,500 years argued the AMOC was now at its weakest in at least a millennium, so the slowdown was documented, measured, published, peer-reviewed and replicated. That part of the story was done. What nobody could nail down was what any of it meant for the question that actually mattered. How close is close? The AMOC has a tipping point, a level of freshwater input and temperature gradient at which the system doesn't just weaken further, but stops self-sustaining and collapses. Scientists knew this threshold existed. Paleoclimate data showed it had been crossed before, during past glacial periods, with brutal consequences. But the threshold itself, where it sits on the scale, and how far the current system is from reaching it, that remained genuinely unresolved. The models of the time weren't built to answer that question. They could simulate the broad strokes of a weakening circulation, but they lacked the resolution to capture the fine-grained fluid dynamics at the moment of transition. The distinction between dangerously close and centuries away was invisible to them. That is the specific gap the Utrecht team set out to close. Not whether the AMOC could collapse, that was settled. Not whether it was weakening, also settled. But what collapse actually looks like from the inside, beat by beat, so you could recognize the signature, while it's still early enough to mean something. So, they built the most detailed model of the Atlantic anyone had ever attempted. Not an upgrade to an existing framework, a ground-up simulation at a resolution the field had never run before, fine enough to track the actual fluid mechanics at the moment a circulation begins to fail. The kind of precision that doesn't come cheap. 6 months on a supercomputer. To put that in terms that land, the same calculation on a standard laptop would take 14 million years. The team at Utrecht wasn't running a quick scenario. They were burning through institutional computing time on a scale that only makes sense if you believe the question is urgent enough to justify it. What justified it was exactly the gap the previous act described. Older models could sketch a weakening AMOC in broad strokes. They could show you a circulation that slows, that thins, that loses force over centuries, but they ran at resolutions too coarse to catch what happens at the hinge, the specific moment when a gradual weakening stops being gradual. The fluid dynamics that govern that transition are small-scale, fast-moving, non-linear. You need resolution fine enough to see them, or they vanish into numerical averaging and you miss the whole story. The Utrecht simulation was built to see them, and when it ran, it found something no prior model had ever captured. A collapse that doesn't look like a steady decline. It has a shape. A specific, identifiable two-stage shape. Stage 1 is long, about 400 years of slow drift, the circulation weakening incrementally, losing strength, shifting position but never crossing a threshold that triggers alarm. From the outside, it looks like a troubled system that's still fundamentally intact. If you were watching in real time, you might convince yourself the slowdown was manageable, recoverable even. Then, stage 2. Not a continuation of the drift, a different animal entirely. Within roughly 2 years, the circulation doesn't weaken further. It fails. Total collapse of the AMOC in a window so short that on a geological timescale it barely registers as an event at all. The 4 centuries of slow deterioration were not a warning that something bad was coming. They were the first act of the thing itself. That shape, the long drift followed by the sudden break, is the result no prior simulation had the resolution to find. It's not a quirk of this particular model's assumptions. It emerges from the physics, from what high-resolution fluid dynamics actually produce when you let the math run fine enough to matter. The previous models weren't wrong about the direction. They were blind to the structure, and structure is what changes everything. Because if collapse has a signature, a slow drift phase with identifiable physical characteristics, then in principle you can find that signature in the real world. You can check whether you're already in it. That is what the Utrecht team did next. So what does that structure actually look like, in physical terms? Because the numbers are doing something worth sitting with. 400 years of slow drift, then 2 years of total failure. Not slowing to a crawl, total failure. The full circulation, the engine that has been running continuously for longer than our species, has been building cities, stops, in 2 years. The instinct is to focus on the 2 years. That's the number that sounds like a headline. But that instinct leads you to the wrong conclusion about what makes this dangerous. The 2 years is the tail end. By the time the 2-year collapse is happening, the window to respond has already closed. Decades ago. Here's the mechanism the simulation revealed. In stage 1, the circulation doesn't weaken uniformly. It drifts. The whole system shifts. The pathways that cold, dense water follows as it sinks in the North Atlantic begin to migrate, millimeter by millimeter across decades, then faster. The circulation is still running, still moving heat. But the architecture of how it moves is changing underneath the surface in ways that are very hard to see if you're not looking for the right signature. This is the phase that lasts 4 centuries. And during that entire window, if you were measuring total flow volume, the metric we've been using to track AMOC health, you might see a gradual decline and conclude the system is weakening slowly, manageably, in a way that gives future generations time to adapt. That conclusion would be catastrophically wrong, because what the high-resolution physics shows is that slow drift isn't linear degradation. It's a system moving toward a threshold. The deeper the drift, the less stable the remaining circulation becomes, not proportionally, but exponentially. The last phase isn't the steepest part of a long slope. It's a cliff that appears only after you've already walked most of the way to the edge. 2 years from functional to stopped is not a recovery window. It's barely a response window. By the time any monitoring system catches the acceleration, the physics are already committed. That is why the shape is more alarming than the speed. A fast collapse you could at least see coming. This shape hides. Stage 1 looks like a slowly declining graph that a cautious scientist might call uncertain. The geometry of it is almost designed to be dismissed, until it isn't. And the question the Utrecht team then had to answer, the one that shifts this from a model output to something urgent, is whether the real ocean shows any trace of that drift, whether stage 1 has a fingerprint, and whether we're already standing in it. So they went looking. If stage 1 has a fingerprint, a slow specific drift that precedes total failure, then 30 years of ocean measurements should either show it or they shouldn't. This was the test that separated an impressive simulation from an actual alarm. The Utrecht team took the early stage behavior from their model and worked backward. What would that look like in a real, observable ocean current? Not in a temperature average or a salinity reading, but in something you could actually measure with instruments dropped into moving water. What they found they were looking for was position, specifically whether the Gulf Stream's core had been migrating northward over time, because that is exactly what stage 1 of the modeled collapse produces. As the circulation weakens and loses its organizing structure, the current doesn't just slow, it drifts. It wanders north. Then they compared that prediction against the observational record. Satellite altimetry, float data, direct current measurements going back to 1993, 30 years of the real ocean, collected before anyone knew what to look for. And the Gulf Stream's core has moved. About 53 kilometers north since 1993. Not randomly, not with noise that averages out. Steadily, consistently, in the direction the model said it would move if stage 1 were already running. 53 kilometers sounds like a technical detail. It isn't. That northward migration is the fingerprint. It is the same signature the simulation produces during the long, slow drift before the fast collapse. The match isn't approximate. It is the shape the model predicts, appearing in the data the model never saw. This is what makes the Utrecht result different from everything that came before. Previous studies measured flow rate and found it weakening. That told you the system was losing strength. What it couldn't tell you was where on the collapse curve you were standing, whether you were early, whether you were late, whether the slow decline was stable or a prelude. The fingerprint changes that, because now there's a shape to match against, not just a trend to measure. The real ocean is running the same sequence the simulation ran. Stage 1, the 400-year drift that ends in 2 years of failure. And we're not at the beginning of the record. We have 30 years of it already behind us, already matching. The question was whether stage 1 had a fingerprint. It does, and we're standing in it, so stage 1 is confirmed. That raises the only question that actually matters to anyone living on this planet. What does stage 2 look like from the inside? Not in projections, not in model output, in January, in harvests, in the water creeping up a street in Boston. Start with Europe, because that's where the arithmetic is most brutal. The AMOC is the reason northwestern Europe is habitable at the latitude it occupies. London sits at roughly the same latitude as Calgary. Amsterdam lines up with Edmonton. Oslo is north of the southern tip of Greenland. The only reason these places have mild winters instead of subarctic ones is that the conveyor pumps heat north continuously, roughly 1.25 petawatts of thermal energy, the equivalent of 1 million large power stations running without stopping. When that stops, the Arctic wins. Climate models consistently project Western European winters cooling by 5 to 10 degrees Celsius within decades of a full collapse. That's not a bad ski season. That's crop failures in France. That's heating systems in the UK that were never designed for sustained hard freezes. That's a continent whose entire agricultural infrastructure is calibrated to a climate that no longer exists. And Europe is only one thread. The AMOC is part of a global heat distribution system. And when you pull one thread, others move. The Atlantic's overturning circulation is tightly coupled to the tropical monsoons, the rainfall patterns that billions of people in South Asia and West Africa depend on for food and water. The mechanism is atmospheric. A weakened AMOC shifts the thermal equator south, displacing the rain belts that follow it. The Indian summer monsoon weakens. The West African monsoon contracts. These are not edge case projections. They show up in virtually every major model that has examined a collapsed AMOC scenario. And the populations most exposed are among the least responsible for the emissions that are destabilizing the current in the first place. Then there's the coastline problem. And this one is counterintuitive. You might expect that a weakening Gulf Stream would mean cooler water along the US East Coast. Cooler water contracts. Sea levels should drop. The opposite is true. The Gulf Stream acts like a wall of fast-moving water that piles the ocean surface higher in the open Atlantic and lower near shore. Weaken the current, and that wall partially collapses, and the water it was holding back surges toward land. Studies have linked the already accelerating sea level rise along the U.S. Northeast to AMOC slowdown. Cities from Miami to Boston are already managing this. A full collapse accelerates it sharply, independent of global mean sea level rise from ice melt. Two processes compounding, not competing. None of this is happening in a single dramatic moment. That's what makes stage 1 so disorienting. The catastrophe isn't an event, it's an accumulation, a slow shift that looks, at any given moment, like ordinary variation until the 2-year transition arrives, and the variation turns out to have been a migration. Before that 2-year transition arrives, if it arrives, there is a set of objections worth taking seriously. Not because they dissolve the concern, but because the people raising them are not wrong, that legitimate uncertainty remains. And uncertainty here is not a reason to relax. The first objection is about the model itself. The Utrecht simulation is the highest resolution run of its kind, but highest resolution is not the same as complete. Ocean climate models still can't fully capture certain small-scale mixing processes, the way turbulence moves heat and salt at the centimeter level, aggregated across an ocean basin over centuries. The Utrecht team knows this. They would say so. The model's collapse signature is real and internally consistent, but a model is still a simplified physics engine, and there are forcing mechanisms it approximates rather than resolves. The second objection is about the fingerprint match. The Gulf Stream's 53-kilometer northward drift since 1993 fits the simulation's Stage 1 pattern. But correlation between a model output and an observational record is not the same as proof of mechanism. Other researchers have pointed out that ocean current positions shift for multiple reasons: decadal variability, wind patterns, stratospheric dynamics, and that 30 years of satellite data is a short baseline for a system operating on timescales of centuries. They are correct that the match is suggestive, not conclusive. A third, older objection concerns the tipping point itself. Some modeling groups have argued that the AMOC is more stable than the Utrecht results suggest, that the system has natural restoring forces which previous high-emission scenarios underestimated, and that a full collapse is a tail risk rather than a central trajectory. This debate has run in the peer-reviewed literature for the better part of 2 decades and has not been resolved. All of that is true, and here's what it means. The uncertainty does not point in one direction. A model that can't capture all small-scale mixing might be underestimating collapse risk just as easily as overestimating it. A 30-year observational baseline that fits Stage 1 could be the beginning of a signal or a fragment of noise, but if it is a signal, we are not in early detection. We are already in it. Stability arguments that rely on restoring forces assume those forces activate before the threshold, not after. There is no version of honest uncertainty that amounts to probably fine. The debate science hasn't settled is real. What it hasn't produced is a credible case that the system is safe. Skeptics and the Utrecht team are arguing about how confident to be and how soon. They are not arguing about whether the AMOC matters, whether it is weakening, or whether the consequences of collapse would be severe. On those 3 points, the field is in agreement. The argument is in the margins of a document everyone is reading the same way. So the debate lands here. Everyone agrees on the direction. Nobody agrees on the direction. Nobody agrees on the distance. And that distinction, knowing where you're headed without knowing how far you've already traveled, is its own kind of problem because it makes every decision about response feel premature right up until it isn't. The honest answer to when is we don't know. The Utrecht team found the signature of Stage 1 in the observational record. They did not find a date. What they found is a process, and a process, by definition, is already moving. What they cannot tell you is whether the remaining distance to threshold is measured in decades or in centuries. That gap exists partly because of what we're measuring and partly because of how little of it we have. The rapid array, a line of moorings stretched across the Atlantic at 26 degrees north, has been recording continuous AMOC flow since 2004. That's 2 decades of data. It is genuinely the most important oceanographic monitoring infrastructure on the planet, and it covers roughly 5% of the time window the Utrecht simulation spans. Asking it to locate a tipping point is like trying to map a coastline from 20 steps. There are also gaps in geography. One transect at one latitude captures one cross-section of a system that runs through the full depth of the Atlantic, from Iceland to Antarctica, responding to forcing at every point along that path. Freshwater input from Greenland melt is accelerating. Deepwater formation sites in the Labrador and Nordic seas are changing. Each of those feeds into the system at a different point, on a different time scale, and the monitoring of each is uneven at best. What would have to change to sharpen the forecast? More moorings, more depth coverage, longer baselines, none of which appear on any funded roadmap at the scale required, and better models, simulations with enough resolution to capture the small-scale mixing that current climate models still parameterize as rough estimates. The Utrecht run was the highest resolution attempt ever made, and it took 6 months on a machine most institutions don't have. Scaling that up to ensemble runs, the kind that give you probability distributions rather than a single outcome, remains a computational problem without a near-term solution. So the clock is running. We know it's running. We have identified what the first stage looks like, and we are looking at it in the real ocean right now. What we cannot read is the face of the clock, whether it shows years or generations. And that uncertainty, unlike the ones the skeptics raise, does not cut towards safety. It just means we are navigating without the one number that would change everything. That number, the one that would change everything, is the only thing we don't have. And here is what we do have instead. We have a simulation, the most detailed ever run, that showed for the first time what collapse actually looks like from the inside. Not a single dramatic failure, but a process, slow, quiet, already running, that tips into catastrophe only at the end. We have a fingerprint from that simulation, a specific physical signature that marks stage 1, and we have that fingerprint right now in the real Atlantic Ocean. The Gulf Stream has moved 53 kilometers north since 1993. That is not a projection. It is a measurement. For most of the history of this research, the word collapse was a future tense word, something that might happen, something models suggested was possible under certain emissions pathways, subject to considerable uncertainty, pending further study. It lived in the conditional, the grammar of things that haven't started yet. The Utrecht data changes the tense, not because it tells us when stage 2 arrives, but because it tells us stage 1 is not a warning, it is not an approach, it is a description of the present. The process the simulation predicted, the long, slow northward drift of the current before the bottom falls out, is the thing we are currently inside of. The clock isn't counting down to the collapse. The collapse, by the model's own definition, has already begun. What that demands is not panic, and it is not paralysis. What it demands is honesty, specifically the kind of honesty that is hardest to maintain in public life, which is acknowledging that the window for acting before something starts has already closed, and that what remains is acting during it. That means monitoring at a scale we haven't funded. It means models at a resolution we haven't built. It means treating the AMOC not as a distant risk to be managed in future policy cycles, but as a system that is actively changing, right now, in ways that will determine whether hundreds of millions of people face slow agricultural disruption or rapid, irreversible catastrophe. The scientists who ran this simulation are not alarmists. They are people who spent 6 months of supercomputer time trying to see something more clearly. And what they saw was a process that does not pause for political timelines or budget negotiations. The ocean does not care about the debate. It is already in stage 1. The question that remains, the only one that matters now, is whether we are paying attention clearly enough and moving fast enough to act before stage 1 ends.